Okay, continue. It's going to be General Chemistry Part 22. Now we continue our reactions. The third kind, we're finished two types of, alright, and then we gave some examples. Now we come to the third kind of the chemical reaction called a combustion reaction. Now what is the definition for that? The combustion reaction is referred to the organic compound, most of the hydrocarbons, and the burning the oxygen, including nitrogen as well, to generate what? Generate two very typical products. One is carbon dioxide gas, another one is water vapor. Why is not water liquid? It's water vapor because you're burning the gas in the burning chamber, the temperature is so high, the H2O is going to be in the vaporized state instead of a liquid state until it condenses liquid if the temperature drops down, right? So at the high temperature, it must be gas. That's why I always emphasize the physical states for the substances before and during and after the reaction is quite vitally important. Now that is one example right here. So two typical products, carbon dioxide, CO2, and H2O, right? So let's give you an example. Natural gas, methane. All right, in English we call, Dake says methane. All right, that's fine. And the CH4. We already introduced the structure of a methane, right? Last session. And there's a tetrahedron. And then covalent bond burns in the air, in the atmosphere. In the air we have 21% by volume of oxygen gas and 78% of nitrogen gas. All right, by volume. So the chemical reaction equation is such: CH4 is gas, react with plus means react, and oxygen gas, and a one-way street to the products carbon dioxide gas and water gas vapor, right? Because temperature is way beyond 100 degrees of a boiling point of water, right? So the water is going to be heated into the vapor, right? Or the steam, right? Now look at this problem, this equation. Now it is different from what we just introduced prior to this. We talked about the very first one called single displacement, right? In that case, we have two possible products. One is a gas, an evolution of a gas, right? And out of the chamber, right, out of the beaker. We sometimes call that gas formation reaction, right? Now, what's the difference between gas formation reaction and then the water vapor, and then the carbon dioxide as gas? Is this also considered as a considered as a gas formation? No, it is not. Because why? Why? Because this is not the gas only as products from the reaction starting from non-gas. So the reactants are already gas, gas, and the gas, oxygen, and then you form a gas that's not considered as gas formation. Gas formation normally refer to the reaction with reactants as a solid or liquid or solid or aqueous solution, and then when they react and then they replace the hydrogen gas, right, hydrogen atom out of the hydrochloric acid, the first example we have already discussed, and then it generates hydrogen diatomic molecule, right, gas molecule. That's considered as gas formation reaction. Now here is gas. Now of course if you have alcohol, right, ethanol, we already did that in the past, and the burning oxygen form gas, you can say that's gas formation, right? But I would think this is combustion, right? Combustion. Now that's first. The second is this reaction involve electron transfer. Right? We already did this in the past. So let's repeat it briefly. So check out the oxidation states of each element involved in the reactants and the products. Right? So carbon, hydrogen, combined with a non-metal, normally the hydrogen appear to be plus 1 as oxidation state. And the oxygen diatomic molecule, both are identical oxygen atoms. None is stronger than the other for the electron pair, the bonding pair towards itself. So they 100% shared at an equal distance between two nuclei, and that's the diatomic molecule, the covalent, and the oxidation state for either oxygen atom is 0. So let's put down here. So this one, hydrogen is plus 1, and then this is 0, right? And then if this plus 1, 4 of time, right? 4 of them give you plus 4, right? Plus 4. And then this carbon must be what? Must be negative 4. Negative 4. Oxidation state. Now check it out. The carbon on the other side of a reaction equation as product. Carbon dioxide, oxygen 99.9% of chance it form compound, which we call oxide, right? And appear to be -2. So it's -2. So -2, and you have how many? You have 2 of them. So total is -4, right? -4. If these two present -4 as oxidation state, then this carbon must be what? +4, right? Because it's neutral, right? So it must be +4. So reach a neutrality for carbon dioxide. So look, the carbon before and after reaction occurred, its oxidation state. Its oxidation state changed from -4 to +4. How many electron transfer involved? We did this a long time ago in this class. We draw a number line. Remember, if you remember. Let me do this here. We have space here. So if you have a number line, right? Number line, right? And this is positive infinity, right? Here is negative infinity. We don't have to. But in the middle is 0, right? It's a neutrality now, but it's not. That's a 0, right? And then the carbon in methane start from -4. So 1, 2, 3, 4. So -4 right here. And then become carbon dioxide, the carbon will present as +4. So 2, 3, 4, +4. Right? From -4 to -3, how many electron transfer involved? We lose 1 electron or gain 1 electron. For -4, you gain 1 electron, become -5, right? So you, instead of -4 become -3, you gotta lose 1 electron. Lose 1 electron is to subtract -1 as the charge of the electron. So double negative, -4 plus 1, that become -3. So you go that way, you lose electron. Every single number, every integer number representing 1 electron get lost. So from here to there, so how many electrons? 1, 2, 3, 4, 5, 6, 7, 8. So 8 electron, right? 8 electron transferred, right? Between carbon and something else, right? Carbon beginning with -4 and with +4, where did the electron go? If the carbon start losing electron, right? That's the way you lose electron. Lose carbon loses the carbon, right? Oh, no, that's not. The carbon atom in methane, right? Right? Lose 8 electron. To who? Let's check that. Now, the carbon does change. What about hydrogen? Hydrogen +1 on left hand side as reactants. What about hydrogen on right hand side as part of the components of the water as products? Now we know that. Oxygen in the water is -2. And this hydrogen must be +1 because you have 2. So then you reach a neutrality. +1 times 2, right? That's +2. So the hydrogen, before and after, it does not seem to change its oxidation state. Which means the hydrogen does not gain or lose electron at all in the entire process. So how many elements involved in this reaction? Carbon, hydrogen, oxygen. Only 3. If the hydrogen did not take or lose the electron, has nothing to do with the electron transfer, who the hell gonna be the one take the electron from carbon? Gotta be oxygen. Now look at oxygen. Now let's check out oxygen. Oxygen starts from 0. 2 of them. Now on the right hand side, it says -2, right? Yes, -2. So from 0 to -2, what? 0 to -2 is going this way. This is going that way, right? Going that way, right? And the oxygen is going from here to here. From 0 oxidation state, become -2, right here, -2, right? -2. Now each way you gain 1 electron, right? For 1 integer number, and you gain 2. So each oxygen atom gain 2 electrons. Now where do 2 electrons come from? Come from 2 out of these 8, right? So electron transfer between what? Electron transfer hand to hand between carbon atom and the oxygen atom, right? How many oxygen involved? 2 here. But here's how many? 1, 2. No, 3. So it's not balanced. Now we need to find out why, because if you have 8 electrons lost, give away from the carbon, got to have somebody take this 8 electron to maintain what's that? Conservation of energy, correct? So if you only have 3, you got to increase. But look, we balance the equation in my handout, right? I say, if you balance the equation, the first step, you balance metal. If you check the tips, right? The metal elements. If the compound doesn't have metal as the reactants, right? You balance what? I mean, in the entire reaction, there's no metal involved. You balance hydrogen. Then you balance non-metal, and then you balance all these mono element, diatomic, molecule like a gas H2 and N2 and O2, chlorine Cl2. Those will involve only 1 element. Those molecules, you can increase or decrease the multiple of their numbers. It doesn't change the multiple of other elements involved in the compound. If it's a compound, by the way, you double 1 element in the binary compound, and the other elements will be doubled as well, right? So you destroy balance, you get it chaotic. So we do this, and that's why we put oxygen at the end, because oxygen also has a feature, it always 99%, it does not change its oxidation state during the reaction as -2, right, most of the time. So now we check. 8 electron out of 1 carbon, right? Then that 8 electron must be taken by the oxygen, and each oxygen can only take what? Only take 2 electrons from 0 to -2, right? 0 to -2 right here. From 0 to 2. So we need what? We need 4 oxygen atoms. Now each oxygen diatomic molecule, right, got 2 oxygen atoms. So we have double it. So we must double this to make 4. Now if you double this, then this is an even number, this even number, that's our number, that's okay. If we double this, then make 4, right? So we double this. Now if we go back, go by my tips, is there any metal involved in this reaction? No, no metal. So the second elements we suppose balance on is the hydrogen. So we balance hydrogen. 4 hydrogen on this side, if only 1 in front of the as coefficient, there are only 2 hydrogen. So we need what? We need double the number of water molecules, so make it 4 hydrogen atoms. So 4 to 4, that's even. And if you double this, then you double the oxygen, become 2 oxygen atoms, and here to the 4 oxygen. So here, before you balance it, that's only 2, so you can double that. That's the order you make balancing the reaction equation easier and quick. And then involve less error, right? Now we understand. So in this case, the 8 electrons were lost from the carbon in methane, right? So the carbon becomes the carbon atom in carbon dioxide. Those 8 electrons, right, will be taken by who? By 4 oxygen atoms in 2 oxygen gas molecules as reactants. Become 2 oxygen atoms in carbon dioxide and 2 oxygen atoms in 2 water molecules. 2 water molecules. You see that? So that is how the energy conservation is achieved and the mass doesn't change. We got the same mass, we got the same number of atoms of same elements on either side, right? That means the mass balance and the charge also balanced. So that's how the 8 electron were given away from carbon, taken by 4 oxygen atoms. So that's how we find out. So when oxygen atom in oxygen gas, right, taking electron away, right, it means it oxidizes the carbon. And the carbon loses electron, right, being oxidized by oxygen, and itself become a reducing agent to reduce who? To reduce the oxygen. You see that's a relationship, right? You and me and you lose, I gain, you lose, you know. And then what do you call agent? What do? You be what kind of agent, right? You're taking electron away, you be the agent for taking electron away, right? So in this case, we call reducing agent or oxidizing agent. Now, who is the oxidizing agent, right? Oxidizing agent is the species, right, taking electron away from somebody. Of course, it's oxygen, right? And who's the reducing agent? Of course, carbon, right? Who getting oxidized? Carbon getting oxidized. Who getting reduced? Oxygen getting reduced. Now, oxygen getting reduced, the number from 0 to the left-hand side is that decrease. Decrease means reduce. So that was reduction as a noun come to play, right? And the oxidizing, and you take the electron away, and the electron's negative value particles, right? Like you are a person who have a very negative attitude, and people sometimes would be advise you from their good heart, right? To tell you, hey, don't be so negative. Try to lose it. Lose what? Lose the negative attitude. Become what? Become a positive person. A positive person everybody likes, right? If a negative person, everybody stay away from them. Because sometimes getting nasty, right? Nobody want to involve that kind of a situation. So, try to lose something. Lose what? Losing electron means you're getting more value along the number line towards the positive side. Okay? So now it's very clear. So this kind of reaction is not called gas formation. So you can define, right? Is it the combustion reaction can also called, right? We remember that column. Also classified as what? Classified as what? As redox, right? Redox reaction, right? But not gas formation, right? But not gas formation reaction. Right, very clear. All right. That's the third kind of combustion reaction, right? Combustion reaction. All right. Now the fourth kind. All right, fourth kind. So time 11 minutes. Okay. Now there are two very simple. Now this is a combustion reaction, and then we may give you some practice problem in the homework number 10, and will be given to you probably tomorrow or Saturday, and to do next week, right? And the final will be next week, sometimes Friday or Saturday, latest possible time, so we have more time to learn a little more, and before we call the end of this class, right? Because the crisis of virus. All right, so now let's talk about the other type of chemical reactions. And then there's called synthesis. Synthesis is a reaction. The reaction started with a simpler, right? Simpler substances, right? And produce a more complicated substances, right? So that's called synthesis, right? Synthesis reaction. So reaction starts from simpler species simpler substances. Right. To be composed into, or combined composition, right? Or decomposition. Composed into more complicated products. So synthesis. Now what happens when we talk about synthesis? So you have this in general. In general is what? In general is going to be A, right, plus B, right, and the C, and then give you the combination, right? Combination of what? A compound with all three A, B, C. Now that is the generalized format for composition, right? And of course, there's another one is the opposite. Called a decomposition reaction. Now that's going to be the other way, right? All right, so let's see if we are able to give some example for synthesis, right? Synthesis reaction. All right, so we'll give some example right here. Let's put here as 4. All right, and then examples. All right. So what about something we cannot live without? It is called what? Water. Now we try to use the simplest possible compound to explain the concept to the details, right? So what about hydrogen gas? What is hydrogen gas formula? H2 gas, right? Right? Burns in the presence of what? Of oxygen gas, right? O2, to form. What is that? H2O. Now first, of course, is going to be the gas, right? And the condensed liquid. Let's put gas instead of liquid. All right. That's going to be better. So, if that's the case, we are able to figure out H2 gas react with oxygen gas. And then it's a one-way again, one-way street, right? And then give you water, gas, because the temperature is so high, it burned, right? And the reaction burned, so I put triangle down there, means heating. But this is not just heating, it's a very high temperature. And then, so that they can combine. So what happened? Is that balanced chemical reaction? Now the simpler one, a little bit complicated. This is just a monoelemental diatomic molecules, both. And become a what? Binary compound. It's a little bit complicated. So that's synthesis. Now was it balanced or not? Let's go by the tip of balance equation. We not have enough time to cover too many examples for learning the tips of my tips of balancing chemical reaction equation, right? But you already have my handout, so please read it, please understand, please follow up each example to understand every step. And then do some practice and on your own, and then you will be better off. Alright, so here we balance hydrogen, right? Is hydrogen balanced? 2 hydrogen on the left, 2 hydrogen on the right. Seem to be balanced. But what about oxygen? Oxygen, there's 2 here, but only 1. So we have to what? The even number, the odd number, we have to double it. Double it. When you double this water molecule, because it's binary, you involve the hydrogen. The balanced hydrogen atoms, again, are broken down, right? So it's 4 here, 2 here, so it's not balanced. We have to rebalance it, so we double it here. Right? So that is the case. Now what happened to this? Because this reaction can go one way because, and it's also a redox reaction, and we're going to analyze it in just a minute. And then we'll have water is much more stable than the hydrogen and the oxygen gas. You know that. Right? Hydrogen is very flammable, right? Very, very vulnerable and dangerous. Right? If you don't know, I would suggest you to go online, check. I think 1936 Hindenburg airship, right, from Germany, right? And then arrived in New Jersey, all right, across Hudson River from New York. And then just about landing, and then suddenly a lightning struck, and then it caught fire in 40-50 seconds. Entire huge airship burned into ashes, right? 40-some people lost their lives, right, in less than 1 minute. Now, is that airship? No, it is not airship. It is a gas ship. What kind of gas in there? Is hydrogen gas filled up with a airship. Why they use this flammable, dangerous hydrogen gas? Very, very unstable, because that's just prior to the World War II, and the Nazi Germany tried to utilize every possible resource to build a war machine, and then so other country, right, the League of Union tried to stop it, and then so put on embargo of shipping helium to that country. And then Germany does not have helium to make a helium airship, so they bailed on it, and then was hydrogen, but I don't know if somebody struck a match or light up a cigarette inside, or just a lightning. The whole ship burned down to ashes within 1 minute, and 40-some people lost their life. Now that's very vulnerable, very dangerous. It's not stable, nor as oxygen. Oxygen is the gas. Help the burning, help the ignition, help the combustion, right? Oxygen. And then, so if there's a fire going on, you blow oxygen there, and the temperature of the fire was going up, all right? So it is also very, very vulnerable, very, very dangerous, very, very flammable. It is not a stable compound. But when they combine, these two become water. Then the whole system, H2O, will have much, much less energy as hydrogen diatomic molecule or oxygen diatomic by themselves. So the entire system will going down to a lower energy level, and then the two water molecule, even it's not water, it's a gas, right, at high temperature, will be much more stable than the two diatomic molecules. So in this particular case, the reaction, combustion reaction, the delta H must be a negative value, but I don't know.